Yeah. And this goes up to here, perhaps. No? Up to here is okay?
Yeah, no, that's fine.
That's okay.
Okay, welcome to this second lecture. Professor Dipendra Prasad will continue with Dan Gross Prasad lecture.
Yeah. All right, so thank you. So yesterday, no, day before yesterday in my previous lecture, I was talking about local Langlands correspondence, which gives a way to parameterize representations of a real and periodic group. In terms of parameters. Parameters which are homomorphisms from the Weil-Deligne group to the L group. So I introduced this notation pi g, set isomorphism classes of irreducible representations of GF, and there was this sigma G conjugacy classes of morphisms from W prime F to G. So this is same as what is called the dual group G hat C, semi-direct product with WF. And what the local Langlands correspondence says is that to every representation there is a parameter, and somehow it can be refined to make a bijection of these two sets. So that is called the refined local Langlands correspondence. So for doing the refined, refined local Langlands correspondence, it's better to begin with G, a quasi-split group. So I will begin with a group which is quasi-split over F. And one reason to begin with quasi-split groups is that the refined local Langlands correspondence is sensitive to fixing an additive character from the maximal unipotent subgroup to C star. A fixed non-degenerate character on the maximal unipotent subgroup of GF. So this goes under the name of Whittaker datum. So one needs to fix Whittaker datum. So this is called Whittaker datum. Needs to be fixed. You know, for certain matter, the choice of psi doesn't matter for certain matters because psi is unique up to conjugacy. But for certain groups, it is not unique up to conjugacy. And then you need to fix one, and the bijection depends on that fixed choice. Just to give you an example, for GLN, any two Whittaker datums are conjugate by B, but for SL2, they are not conjugate by B. So SL2 theory is a bit subtler than the GLN theory. You need to fix the Whittaker datum, which for which there are many choices which are different. So I already said last time that one looks at the disjoint union of pi g alpha. So here G alpha are pure inner forms of G, which I will not define here, but then I will give examples relevant to what we will need. So there is this, and then there is sigma tilde G. So that sigma G was just morphisms, and sigma tilde G consists of a morphism phi together with chi, where phi is what it was on the previous board, a morphism, and chi is a character of pi naught C phi. So C phi is the centralizer of the image of phi in G hat. And chi is so this is a finite group, and it is a character of this group that you need to, so this is the enhancement. Phi has been enhanced to a pair phi comma chi, and this set of these pairs is called sigma tilde G, and the refined local Langlands correspondence proposed in this form by David Vaughan is supposed to be a bijection of sets. No, no, all. No, the Whittaker datum is fixed for the group, but it is not related to the representations involved. It is used for the correspondence. It is used for the correspondence, but the correspondence is among all representations. Sorry? I did not say isomorphism classes of irreducible admissible representation because, you know, there are theorems due to Bernstein which says that irreducible already implies admissible. Yeah, this is a bijection. No, there is a packet. You know, packet is this information of this enhancement chi. So if you drop the chi, then this mapping is surjective and its fibers are the L packets. If you drop chi, then the mapping is surjective and has fibers, whose fibers are called the L packet, and the L packets are therefore parameterized by these characters. Pi naught C phi is the character group, and if it is an abelian group, then its cardinality is the cardinality of the L packet, of the Vaughan packet. So Vaughan packet means that it is the inverse image of phi on that set. I'm happy to, not clear? An example will help, and indeed I did want to do an example, also an example which is very relevant for the GGP. So example of unitary groups. Unitary groups. So this is unitary group on a Hermitian space V, dimension of V is equal to n. So one might call this unitary group UN, but that notation UN does not do justice to the fact that it depends on V. So over reals, the various forms of the unitary group are usually denoted as UPQ, corresponding to the Hermitian space Z1 bar plus ZP bar, and then minus ZP plus 1 bar plus ZP plus Q bar, and this comes with a minus sign. So the corresponding isometry group is called UPQ, and all these groups are supposed to be what is called inner forms. And for pure inner forms, there is one slight detail. Pure inner forms depend on the isomorphism class of the unitary of the Hermitian space. Class of the Hermitian space. So two pure inner forms may give the same group. Pure inner forms may arise from the same group. So such as UPQ and UQP. So these two groups are the same, but the Hermitian spaces are different, and they are treated as different pure inner forms. Okay, so what the Vaughan packet is supposed to do is to look at representations pi of UPQ over P comma Q such that P plus Q equals N. And so recall that by Harishchandra, there are WG mod WK many discrete series of a given infinitesimal character. So in the case of UPQ, thus for UPQ, number of discrete series And representations of a given infinitesimal character make up what is called the L packet of discrete series for these groups. Number of discrete series in an L packet equals, so WG is the Weil group of the complex group, which is a symmetric group on P plus Q symbols, and WK is factorial P times factorial Q. So there are these many discrete series in an L packet on UPQ. And then the Vaughan L packet will consist of all the discrete series in all UPQ. And therefore, you have to add these numbers up. And these are the binomial coefficients. And when you add them up, you get a nice expression for number of representations in the Vaughan packet for the unitary group. Thus, number of representations in the corresponding Vaughan L packet equals summation of P plus Q factorial upon P factorial Q factorial. Here P runs from 0 to n, and that is nothing but 1 plus 1 to the power n, which is 2 to the power n. And what the local Langlands, the refined local Langlands correspondence is saying that this set of representations is in bijective correspondence to character of the component group. So now I have to introduce the L group of the unitary group. This is supposed to be nothing but GLNC, semi-direct product with Z mod 2. And this semi-direct product is taken by G goes to Pn, G transpose inverse, Pn inverse, where Pn is this matrix 1, minus 1, 1, minus 1, dot, 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 minus 1 to the power n minus 1. So this is the L group of the unitary group. And the parameter is a mapping from WR to L group of U, which is GLNC semi-direct product with Z mod 2. And this WR contains WC, which is C star. So a mapping from WR to GLNC semi-direct product Z mod 2, when restricted to C star, is just a homomorphism from C star to GLNC, and therefore it is sum of n characters. Because it extends to a homomorphism of WR, those n characters are what are called conjugate self-dual characters. So P restricted to C star is chi1 plus chi-n, where chi-i's are conjugate self-dual characters. The characters of C star. By conjugate, one means that chi-i inverse is chi-i sigma. So on C star, there is the Galois action, Z goes to Z bar. And this means that this is if and only if the character restricted to R plus is trivial. R plus or maybe, yeah, R plus. So these are called conjugate self-dual characters. And in fact, the restriction to C star determines this phi up to conjugation. So this information is complete information. For n even, these conjugate self-dual characters are supposed to be what are called symplectic characters. And for n odd, they are called orthogonal conjugate self-dual characters. So conjugate self-dual characters come in two flavors. Self-dual are conjugates orthogonal and conjugate symplectic. Conjugate symplectic and conjugate orthogonal means that these chi restricted to R star are trivial, and conjugate symplectic means that chi restricted to R star are non-trivial. They are trivial on R plus but non-trivial on R star. So this is the parameters for unitary groups. A parameter for unitary group is just sum of n characters of C star. Parameter phi for a unitary group is a mapping from WR to the L group of U, which is this. And this is equivalent information to just saying phi restricted to C star as a sum of conjugate self-dual characters. And then there is a calculation which one makes is that the component group of phi is Z mod 2 to the power n. So pi naught of C phi is equal to Z mod 2 to the power n. Okay, so chi is our self-dual and discrete series represent a discrete series parameter if and only if chi I and chi j are distinct. So these are n distinct conjugate self-dual characters which are orthogonal for n odd and symplectic for n even. And the component group is Z mod 2 to the power n. And we already know that there are so many discrete series representations. So what one is saying is that giving a character of the component group gives rise to a particular representation of UPQ. So thus in this case, giving a character of pi naught C phi is equivalent to a unitary group UPQ, group UP comma Q, together with a discrete series representation. So, of course, when Vaughan proposed his conjecture, he, of course, knew all the theory, which was basically reformulation of Harishchandra. So this fact was well known to people in real groups. That character of the component group gives rise to a form of the unitary group in this case and a discrete series on that unitary group. So in particular, what it means is that a character of pi naught C phi tells you which there is a certain unitary group which is associated to that. No, kernel of the character is character from Z mod 2 to the power n to Z mod 2. Kernel is elementary abelian group of rank n minus 1. But what one might say is that not only, so this is what one may call a framed group. It comes with a natural basis. And then you may look at character on which basis elements it is trivial and non-trivial. And that gives you P comma Q. So indeed, P comma Q can be gotten there. And then you will see that certain of these characters, so therefore that Z mod 2 to the power n, in fact, is parametrized by these chi-i's. And on some chi-i's, it takes the value 1. On some other chi-i's, it takes the value minus 1. And then you construct a discrete series representation. Okay, good. No, we are talking about all representations, Rajan. Langland's correspondence is all, including the trivial representation, including the finite dimensional. Okay, so now we will get back to GGP. So back to GGP. So, I indeed give this example of unitary groups, which is part of GGP, but for today at least, I will talk mostly about orthogonal groups. So we begin with SOV and SOW, this pair of groups, and W is a subspace of V, quadratic spaces, non-degenerate subspaces, non-degenerate subspace. Of codimension 1. And as I have been perhaps talking in each lecture, the GGP problem is to understand the restriction of a representation of SOV to SOW. So I have already made a slight change of notation, and at some point I call SOV as G and SOW as H, but I think it is more convenient for me to take this as G and H to be diagonal SOW. And the question that we are trying to understand is pi an irreducible tempered representation of G. So therefore, pi itself is pi 1 tensor pi 2 when is harm pi comma C over H non-zero. So recall that from AGRS, dimension of the Helm space is less than or equal to 1, and we want to know when it is 1 and when it is 0. So So assume, just like in the refined LLC, I said we prefer to begin with quasi-split groups. We will assume that this pair is quasi-split. So assume G is quasi-split, which means that which means okay, for SO2n plus 1 corresponding to a vector space V, there exists an isotropic subspace of dimension, isotropic subspace of dimension n. There is a n-dimensional subspace on which the quadratic form is identically 0. Such an isotropic space is unique up to conjugation by Witt's theorem, and such a quadratic space is more or less unique. And for SO2n, one can go down up to n, which would be split. There exists an isotropic subspace of dimension greater than or equal to n minus 1. So if it is n, then it is called a split. If it is n minus 1, it is quasi-split but not split. So we will assume this. So to say, this is the base point. And okay, so here pure inner forms correspond to same discriminant. So SOV and SOV prime are said to be pure inner forms of each other if V and V prime have the same discriminant. Okay, so maybe I should have begun this part of the lecture by quoting a theorem from quadratic forms. So maybe I quote this theorem. A quadratic form over a local field, form over a local field has two invariants. One is called the discriminant, which is an element in K star mod K star square. And the other is what is called the Hasse invariant. Which is a element in plus minus 1. And these two invariants uniquely determine the quadratic form. And therefore, if we are looking at quadratic forms of the same discriminant, they differ by the Hasse invariant. And therefore, for number of pure inner forms of an orthogonal group are two of them. Same discriminant, but the Hasse invariant, both options are allowed. And therefore, the pure inner forms of G are four of them. You can change it on V and you can change it on W. So of SOV on V, and thus there are two pure inner forms of SOV. And therefore, there are four pure inner forms of G. Thus, there are four pure inner forms. So there is the notion of what is called relevant pure inner form. So, this pure inner form is, therefore, you change SOV to SOV prime, SOW to SOW prime. But since we are doing the branching problem, we are not only interested in changing the groups, but changing the groups so that the smaller group is contained in the bigger group. So this is what is called the relevance condition, which means that among these four inner forms, we are only interested in those pure inner forms for which the smaller group is contained in the bigger group. And that cuts the number of pure inner, so that is called the relevance condition, that the pure inner form that you construct is of the smaller group of SOW is contained in the pure inner form of SOV, and that condition is called the relevance. And so out of these four pure inner forms of G, exactly two are relevant to the problem at hand. To the problem at hand. So, we have begun with a pair of quadratic spaces V comma W, which we are assuming is a quasi-split pair. And then this defines you a group G. And then there is another one, maybe we call it VA, WA. And that will define you another pure inner form which is relevant. So one of the conditions for the pure inner form is that the discriminant here is the same as discriminant there. Discriminant of V equals discriminant of VA and discriminant of WA, and the fact that WA is contained in VA. Okay, so here then is the weak form of the GGP. So weak GGP. So we are going to look at the Vaughan packet of representations of G. And it says that the dimension of the Hom space of capital pi comma C over SOW plus dimension of the Hom space of pi A C over SOWA where capital pi stands for the L packet of representations of G containing small pi. Small pi. And this notation Hom capital pi comma C, of course, depends on the obvious convention that this is Hom of pi I comma C, where pi i's are members of capital pi. Pi A is the corresponding representation in the Vaughan packet on the other group. Vaughan correspondence, you recall, it goes to parameter space, and the parameter space has an inverse image which is contained in representations of all pure inner forms. It is the Jacquet-Langlands correspondence. One might say generalized Jacquet-Langlands correspondence is a correspondence between representations of two groups which are inner forms of each other. And here it is made more precise in this refined local Langlands correspondence. Any two groups which are inner forms of each other have the notion of a Jacquet-Langlands correspondence. Any two groups. But here we are looking at pure inner forms, and then this correspondence can be made more precise. Okay, so what it means is that this theorem of Eisenberg, Gurevich, Rallis, and Schiffman is not only true for individual members in an L packet, but also for the direct sum of representations in an L packet. And moreover, you are also allowed to go to not only an L packet, but what is called the Vaughan packet, in which you add over all possibilities over all pure inner forms. So if you were to think about this question for UPQ, then you are going to do the restriction problem, let's say from UN to UN minus 1. You give yourself a parameter on UN, UPQ, and you want to do branching from UPQ to U P minus 1 comma Q or P comma Q minus 1 as the case may be. And given the parameter, you will have a packet on UPQ and a packet on UP minus 1 comma Q. One is saying that not only individual branching is unique, but somehow among all 2 to the power n representations on the bigger group and 2 to the power n minus 1 representations on the smaller group, there is only one branching. Everything else is 0. So this is a very strong form of multiplicity 1 theorem. I mean, to relate to what some of you might know, one particular case of GGP extended in the sense of Bessel models and extended for Bessel models is about uniqueness of the Whittaker model. Uniqueness of Whittaker model is a case of GGP for Bessel models, which I have not talked about so far, but that is a case. And some of you might know there is a famous conjecture of Shahidi that inside an L packet there is a unique generic member. So uniqueness of the Whittaker model is true, but the Shahidi conjecture says that much more is true. Among all representations, each one has dimension less than or equal to 1, but the sum of the dimensions is equal to 1. So this is a very strong form of multiplicity 1, and then the main question GGP would like to answer is that there is a particular representation in the Vaughan packet which carries the invariant form. And now, given the Vaughan's refinement of the local Langlands correspondence, all you need to do is to come up with a character of the component group, which will define you a group and a representation which will carry that invariant form. So once you know refined local Langlands, the only thing to do is to come up with an intelligent character on the component group, and that's not too bad. But it involves arithmetic invariant. So somehow these all looks like problems in representation theory, but the recipe is of arithmetic nature. So that is what I come to now. Clear so far? So the weak version of GGP is a strong multiplicity one theorem. In fact, I must admit that in any case that I know about where multiplicity one is true, strong multiplicity one is also true. So perhaps, but I already said last time that multiplicity one pairs are essentially the GGP pairs, and therefore strong multiplicity one also are the GGP pairs. So the next job is to talk to you about component groups and characters on that. Eric, you want to say something? Similar? Yeah, exactly the same. No, I mean, in some sense, the GGP handle many groups, but the point is that the framework is the same, conjectures are the same, slight modifications are necessary. Component groups are similar, their parameterization is similar. There are certain details which one has to indeed worry about. And some of those details are a bit confusing. So one of the details here is that, I said that the Vaughan parameterization depends on the choice of an additive character. And one has to keep that in mind somewhere. Okay, so I think the next task that, I already for unitary group, I discussed the component group and how nicely it can be parameterized and what is pi naught.
Sensitive to the such will not be true for spin or other.
I mean, you have to always keep in mind that GGPs are true for GL2, but not for SL2. True for PGL2, but not for SL2. Okay, so fine. So, okay. So I need to talk about L group of orthogonal groups. Orthogonal groups. So the L group of SO2n plus 1 is SP2nC. So somehow that's a bit simpler group. Whereas L group of SO2n can be slightly difficult. Because, there was this thing about split versus quasi-split. So this group is SO2n, semi-direct product with the Galois group of E over F. So there is a particular quadratic extension which may be involved. But this group can be identified to O to N, and that helps greatly. So the semi-direct product of SO2n, SO2n has an outer automorphism given by conjugation by O2n, and this group can be identified to O2n, and somehow parameters can be treated as homomorphisms into O2n, which is a classical group. So a Langlands parameter for SO2n plus 1. So, when I write SO2n plus 1, I am not being too careful about the quadratic space. Somehow it doesn't matter too much. Is a homomorphism phi from WF to SP2 and C. So it is a finite dimensional representation of the Weyl group. Weyl group for most purposes is just a finite group, and you can decompose this representation as sum of irreducible. So decompose this representation as sum of irreducible. Yes, as a sum of irreducible representations. So what you do is you write phi as, let's say phi I, okay. So, because it sits inside SP2 and C, this representation is what is called self-dual representation. Phi is isomorphic to phi star. And therefore, when you write it as direct sum of phi I, some phi i's will not be self-dual and others will be. So those which are not self-dual, you write it separately, summation over I. Then there is summation of phi I, where phi I equals phi I star. And then there is this notation or usage made in the subject of good parity. So this parameter phi I has the same parity as that parity. So this is symplectic. And then sum of phi I equals phi I star and phi I orthogonal. So this you have written it as sum of irreducible representations. And now let us put some multiplicities, Ni, Mi, Li. So any representation of any group which is completely reducible inside SP2 and C is a direct sum of this kind. And now we want to look at what is the centralizer of this representation inside SP2 and C. So the centralizer C phi is equal to, so you see phi I plus phi I star, that appears with multiplicity Ni. If you are going to do this inside GLN, then to each irreducible representation, the number of copies it appears, the corresponding centralizer will have GLNI. So roughly that is the picture we are having. So this will be GLNI corresponding to the first factor, corresponding to the second factor, phi I equals phi I star, and it is symplectic. Then it corresponds to O Mi, C, and then there is this SP of Li, E, and then there is a product again. So the component group, which is pi naught C phi, is therefore contributed by this factor. And for each of these factors, there is Z mod 2. So therefore, pi naught C phi is product of Z mod 2. And this product is over phi I equals phi I star and phi I symplectic. Say that again. No, I mean, perhaps I am not putting the proper indices here. This is over a set I, this is over a set J, that is over a set K. But yeah, there is some notational vagueness.
Multiplicity MIs don't. MI doesn't play a role. Is that the question?
Yeah, it is product. Yeah, maybe that is better. This product. Okay. All right, so this is the character of the component group. And similarly, for a parameter for SO2n, similarly, for a parameter phi, P from W prime F to O2NC, you can do the same decomposition. And again, the case of good parity will give rise to orthogonal groups. And the statement is that pi naught C phi is product of Z mod 2, and this time phi equals phi star and phi orthogonal. Good parity. It has the same parity as the ambient group. So the component group of a parameter is parameterized by number of irreducible self-dual representation of the same parity as the ambient L group. And now the task in front of us is to construct a character on these component groups. But these phi's are symplectic or orthogonal representations of the Weyl group. Okay, so let's call the GGP recipe on the character of the component group giving the distinguished representation of the Vaughan L packet such that harm pi chi C over SO W prime, let's say, is non-zero. So to a character of the component group, there is a representation pi chi. That is refined local Langlands correspondence. Character chi of the component group has a pi chi, uniquely determined. It determines a group and a representation. So we need to construct a character of the component group that I have called chi. So now we have to give this chi, and let's call this chi GGP of pi. So this chi GGP of pi is a character on the component group. The representation pi chi is a representation of G, which is SOV cross SOW, and it has an invariant linear form for diagonal SOW. That is the weak GGP. You want to construct that character chi. Okay. So this chi GGP pi, this is a character on the component group, and the component group C phi. So maybe this parameter phi, we can call it phi1, phi2. P is a parameter for G, which is SOV cross SOW. So the L group for SOV cross SOW is a symplectic group times an orthogonal group. One of the parameters phi1 is symplectic, the other one is orthogonal. And this one, so here let's say that phi1 is orthogonal and phi2 is symplectic. So this is indeed one of the important details of the GGP situation, that one of the groups has an L group which is orthogonal and the other one is symplectic. And the fact is that orthogonal times symplectic is symplectic. And so this one, so before I define this, then we know that C phi is product of Z mod 2s, where phi I equals phi I star and phi I orthogonal, phi I contained in phi 1. That corresponds to that phi 1 cross product over Z mod 2, phi I equals phi I star, this time phi I is symplectic and phi I contained in phi 2. So to define this character of the component group, you can define it on each individual copies. So chi GGP, maybe I put pi there and I define it on phi I. And yeah, so this is the epsilon factor. I will come back to epsilon factors of phi I tensor phi 2. So this is an orthogonal representation. This is a symplectic representation. This is an epsilon factor of a symplectic representation. One knows that the epsilon factor of symplectic representation at half are plus minus 1 and independent of the choice of the additive character. So this is good. And then one puts a determinant of phi I. So phi I is an orthogonal representation, and an orthogonal representation has a determinant which may not be trivial. And phi 2 is a symplectic one. So it is a dimension of phi 2 by 2 evaluated at minus 1. So determinant phi I is a character of F star, and this element is an element in F star, so you can evaluate, and that's the recipe. And so I should have made some slight differences here. Sorry. Okay. And chi GGP phi of psi I is equal to epsilon of P1 tensor psi I. Again, it's a very similar recipe times determinant. This time, this is orthogonal P1 raised to power dimension of psi I. This is symplectic. So basically, it's a small variant of the epsilon factor of phi I tensor, the other representation. So this defines you a character of the component group, and by the refined local Langlands correspondence, it defines you a unique representation of the Bogan packet. And that representation of the Bogan packet is the one which comes up in GGP. So I already mentioned that perhaps I will elaborate a few more details about the epsilon factor next time, but epsilon factors used here are for symplectic representations. So epsilon, let's say, of sigma at half. And this takes value plus minus 1. Typically, there is an additive character psi. And then one says that belongs to plus minus 1 and independent of psi. I mean, the epsilon factor of orthogonal representations are supposed to be simple-minded, and there is not too much mystery. The epsilon factor of symplectic representations, on the other hand, are mysterious, and somehow the conjecture uses the epsilon factor of symplectic representations. Okay, so maybe I don't want to go into too much detail about these characters of the component groups which have come up here and which pan out well in some cases, and then of course, the GGP conjectures have been proven in all cases. So that is a theorem that this recipe gives rise to a representation which is the one which carries the H invariant linear form. But perhaps just to interest you in these conjectures, so these conjectures have local features and a global feature, and I just want to make some comments about global GGP. So global GGP says that suppose we are in this situation, SOW contained inside SOV, W contained in V codimension 1 equals 1, now over number fields. So then we talked about the group G, which is SOV cross SOW. And you have an automorphic representation pi here. And then one talks about integral of f dh on this group HA mod HF. And the question is, when is this not identically 0? So the GGP conjecture says that if this is so conjecture 1, if period integral is non-zero. Integral non-zero, then L half is non-zero. Is non-zero. And it is the converse which is most interesting. It says that if L half is non-zero, then there exists a pure inner form. So once again, for part B, we are looking at automorphic representations on quasi-split orthogonal groups. And then there exists pure inner forms. Inner form SO V prime, comma SO W prime, and which are relevant of the quasi-split SOV, comma SOW, such that the period integral is non-zero, such that the period integral is non-zero. Integral is not identically. So out of automorphic forms on quasi-split group and the fact that the L value is non-zero, one wants to say that there exists a unique pure inner form and representations on them for which the period integral is non-zero. So let me say what things need to be done to even make sense of this conjecture. What things? Yeah, right. You need to know that the Jackie-Langlands correspondence makes sense. So what things need to be done even before you can attempt this question? So A, you know, the local GGP for each place of F will have constructed for you a representation, a group SOV, V, capital V, small v, and SOWV. So local GGP constructs IV of GV, which is SOVV, comma, cross SOWV. It constructs local spaces and representations thereof. I already said that one essential detail which one must check, that the local GGP construction gives you a relevant pair. You have a character of this component group, a character of this component group, but those component groups determine you a pure inner form and it may not be relevant. So you must ensure that the GGP recipe is one which ensures that this is a relevant group. So this is part A. Part B, you must ensure that these local spaces glue together to give you a global space. VV and WV constructed by GGP give rise to a global space. So this is often called the coherence condition. Coherence. These spaces are coherent. So which means that now these groups come from a global group. Then the part C is that these representations pi v of now GFV. So now there is a global group and a local representation glue together to give you an automorphic representation. To give automorphic representation of the group G. So in a certain sense, this relevance condition is quite easily built in. This one, one knows how local spaces can be glued together to a global space when the discriminant is given. The product of the Hasse invariant needs to be 1, and that's a simple-minded condition. So this is there. This one is what is the main theorem of Arthur in his book, which says when do local representations glue to give you an automorphic representation? It is what is called Arthur multiplicity formula. And the fact is that these representations glue together to give you automorphic representation for these character of the component group is a simple consequence of the Arthur multiplicity formula. So therefore, these are automorphic, and now one can play this game about the period integral.
A, B, C are there.
Are there?
So you have to show now that the period integral is.
Yeah.
That is
yeah.
What is left, or it's
what is left? What is left? All right. So that's all for the moment. For tomorrow, I was thinking I will do a bit of examples where these things have been studied, and a bit of unitary groups, a bit of Bessel and Fourier-Jacobi models. Yeah, some odds and ends. Thank you for your attention.
Any questions?
Epsilon factors come in the second step.
Sorry?
The epsilon factors come in the second step here.
The epsilon factors are the way the local character is defined. A local character defines you the group GV and pi v. So it comes up in all steps. In some sense, you know, one of the main things that one needs to keep in mind that you have a global symplectic representation pi1 tensored pi2. And that pi1 tensored pi2, the way the component groups are being created, pi1 is orthogonal in my notation, pi2 is symplectic representation. And you decompose pi1 as direct sum of orthogonal, pi2 as direct sum of symplectic. If the global L function for pi1 tensored pi2 is non-zero, then the global L function for pi I tensored pi2 are also non-zero, because that product is equal to the full product. So if product of certain numbers is non-zero, then each one of them is non-zero. These are self-dual symplectic representation, and for them, therefore, the sign is 1. Sign is 1, and sign being 1 is what Arthur needs to make it automorphic. There is, so if you are given a global group G and characters of the component group chi v, then Arthur's conjecture says when this chi v's give rise to an automorphic form. And the statement is that this product of chi v, which is a character on product of the local groups, the local component group, there is a global component group which maps to that, and this character should be trivial on the global component group. That's all. And the global component, so the way they are created are local epsilon and global epsilon, and Arthur will just need that the global epsilons are 1, they are 1 by the GGP recipe, because they are just local epsilons, so it's product. Yeah.
Thanks. And where does the co-dimension one condition come in?
Say that again.
Where does the co-dimension one
Co-dimension one is the classical branching from GLN to GLN minus one or SON to SON minus one. The Bessel models and Fourier Jacobi models, they go deeper using unipotent groups. And it's good that you have shown some interest. Otherwise, I feel a bit guilty to talk about Bessel models.
Thanks.
Any other questions? Okay, let's thank the speaker.